Welcome back. We were doing rectangular approximations. We're going to do, well, one more, and then we're going to do one other type of approximation, which is not technically a rectangular one, but it's a pretty good one. Which we're going to do first is the midpoint one. So this one's kind of a pain because we're still doing these we're still using these three intervals from 1 to 4. Each one is 1 unit long. But now instead of using, you're like, well, the left side was too small, the right side was too big. It's like Goldilocks, right? We're going to use the middle now. We're going to use this point, the midpoint of this interval. So from 1 to 2, we have the first interval, it's 1 unit long. The midpoint is right here. And the issue we had with like the over and the under approximations is like kind of being dealt with here, because like we're missing this part of the area under the curve, but we're gaining this bit, and they're not quite the same, but maybe they're kind of close. So this is going to give us a better approximation. The problem with this approximation is that it's a pain because the numbers are rarely even numbers. And in this case, they're certainly not going to be. So I'm just kind of sketching these. It doesn't really matter if you have a good sketch or not, but it's kind of nice to know and to kind of see, to kind of get the idea that like we're missing this part of the area, but gaining this part, and those are close. So like the goal here is to get to a place where our approximation is actually something that looks more like the area under the curve. So we're going to do it the same way, but this time it's going to be more important for us to use the function to find the heights, because I don't know. Like it looks like the height is 3 here, but maybe it is, maybe it's not. I just drew it that way, right? This height looks like it's a little more than 7. That height, I mean, who the hell knows, right? Like my drawing is not perfect. This is not the exact midpoint of this interval. So like you can't count on the graph here. So we're not going to. We're going to use the function as the height. So basically, we're going to calculate our areas this way. And this is how we did it in the last two, but we didn't really think about it this way. The area of every rectangle is delta x. That stands for the change in x. This just means the width of the interval. But this delta x notation comes up later, so I want you to get a little bit used to it. Delta x means change in x. It means the width times the height, which is going to be some f of x. And usually there's little subscript i's here. I don't want you to worry too much about that right now, but like we're going to use the width times the function evaluated at the midpoint. In this case, it's going to be, that's first one, it's going to be 1.5, because that's halfway between 1 and 2. I'm going to write it like this, f of midpoint. I mean, this isn't a formula you should memorize, but it's like basically we're doing a width times a height. But because the heights are harder to find here, we have to use the function to find them. So we'll label these things A, B, and C again, because that seemed to work okay in the last one. So area of rectangle A is its width, that's the delta x, which is still 1. But now its height is less obvious. So we're going to use f of x to find it. The x value that we're talking about, the one that's halfway between 1 and 2, is 1.5. It's 1.5 or 3 halves. Lots of ways to think about it. We'll call it 3 halves because I like fractions. So the height of this thing is f of 3 halves. I'm just going to write f of 3 halves so that we understand where it's coming from. And f of x is 1 plus x squared. So f of 3 halves. I'm going to stop writing the 1 here because 1 times anything is just a thing. So it's 1 plus 3 halves squared. 3 over 2 squared is 9 over 4. So that's 13 over 4. And you add it to 1. 1 is 4 over 4, 9 over 4, 13 over 4. So that's how we find the area of the rectangles here. We do the width, which in this case, they're all 1s, times the function evaluated at the midpoint. That's how I get this height. Like I said, and these previous two, the heights were like nice round numbers. If we plug those in, we saw that they were the same thing. But now, since our x's are fractions, we can't do it that way. So here's our first area. Area of rectangle B is going to be the same thing. It's width times f of, in this case, halfway between 2 and 3 is 5 over 2. I'm going to stop writing the 1 because I don't need it. And this f of x is 1 plus 5 halves squared. 5 5 over 2 squared is 25 over 4, plus 4 over 4 is 29 over 4. And then the area of rectangle C is its width times the function value at the midpoint. 3 to 4, halfway between that is 3.5, or 7 over 2, which is, again, I'm going to stop right in the 1. I'm just going to do f of x, f of 7/2, which is 1 plus 49 over 4 this time. That's 53 over 4. Now I can sum all those little fellas up, and I get yeah, that's fine. Add all those up. 13 plus 29 is 42. 42 plus 53 is 95 over 4. Try to make sure I did that right. 13, 29, 39, 42, 95, yeah. 95 over 4 is a little bit, it's 23 3/4. And like my hope is that this area that we found here is halfway between, there's like somewhere in between this one and this one. So I had 17 for my first guess, 32 for the, well, 17 for the left-hand one, 32 for the right-hand one. Now this midpoint one got me 23, which is good. Like I wanted this one, I'll write 0.75 for you fraction people. Like this is good. I was hoping this would be in between those. It's like clearly a better approximation than either of the other ones. So this is a pretty good, this is a pretty good job. All right, so that's how we do this. Like I said, sometimes it's not like this, but in this case, the midpoints were fractiony, so I couldn't just read the numbers off the graph. You might not be given a graph. This time I could have done this whole thing without this picture. I just do the width that I chose, which was 1, and then a function value at the midpoint of that interval, and then I plug it in. I plugged it into this function because that's what this one was. And then I add them all up at the end. That's how that works. So last method is called the trapezoidal approximation. And this one, some people might have thought of. It's like, well, rectangles don't work that well because this thing isn't, it's not horizontal. So the trapezoidal one uses the heights at either end of the interval as like the quote unquote bases, and like draws like a straight line there. That second one was better than the first one I did. It's a little hard to tell here, but in this case, the trapezoidal one is going to be too big. Like this curve is like curving below this line. So it's going to kind of look like this. Like a straight line is going to be a better, it's going to go above that. So basically you draw these, instead of drawing rectangles, you draw trapezoids. That's why it's called the trapezoidal method. That's not just a clever title. So you get these 3 trapezoids here. I'll call them A, B, and C again, just for laughs. And you have to remember the area of a trapezoid to do this one. And the area of a trapezoid, of any trapezoid, is 1/2 times the height times the sum of the bases. You may or may not remember that from geometry. But the bases are, like what, there's like kind of, there's 4 sides to this thing. 1, 2, 3, 4. The bases are the 2 that are parallel to each other. That's kind of how we determine it. And the height is the straight line distance between them. And for all of these trapezoids and all these problems we're going to do where we use this approximation, the height in our formula is going to be the width of the interval. Basically, we're taking these little trapezoids here, there's 1, 2, 3, and we're thinking of them as looking like this. Like if you turn this one on its side, it kind of looks like that. And so now this is the height, the base 1 and the base 2. Oh boy, that's a real mess. Let me try that again. the height is this distance here, and the bases are like the two things on the ends. So you can see that the bases, the base 1 and the base 2 are like the heights here. And so that's why it's a little confusing to think about it in terms of height. The height is the width of the interval. The bases are like the f of x's, the f of x values. These are going to be f of x values. But for this one, we can read them off the graph. Don't have to worry about plugging them in because we're just talking about the endpoints are all whole numbers. So let's find some areas. The area of trapezoid A is 1/2 times its height, which is the width of the interval. Remember, we're thinking about it looking like this. So the height is 1. And then times the sum of these two. They're in the trapezoid, their bases, and in the graph, they appear to be heights. I don't want you to like mix up the height here and the heights here, but basically times f of 1 and f of 2, the sum of f of 1 and f of 2. This distance is f of 1. This distance is f of 2. And so you get 1/2 times 1 is 1. F of 1 is 2, and f of 2 is 5. So this is 7 times 1/2, which is 7/2. So just to recap how I did that, I'm using the trapezoidal area formula. The 1/2 is the 1/2. The height in the formula for the trapezoid is the width of my interval, and that's all. And that's 1 in this case. And then the two bases in my trapezoid formula are like the f of x's at the ends of the interval. So I did f of 1, which was 2, and f of 2, which was 5. 1/2 times 2 plus 5 is 7/2. All right, I'll do the same thing for trapezoid B. 1/2 times 1 times, now I need the two ends of the two heights at the ends of this interval, which is f of 2 and f of 3. Which is 1/2 times, let's see, this is 5 and 10, which is 15/2. Very similar process, right? 1 is the width of the interval. F of 2 and f of 3 are these distances, which in the trapezoid formula are b1 and b2. So you plug them in and you get 15/2. Last but not least, we do 1/2 times 1 times f of 3 and f of 4, which is 1/2 times f of 3 is 10 and f of 4 is 17. Is that right? Yeah. So I get 27/2. And now I can add them up and get another approximation. 7 plus 15 is 22. 22 plus 27 is 49/2. That is 24.5. 24.5 if you like decimals better. And again, I would hope that this number is somewhere between the left and the right one. It should be a better approximation. And my left one was 17 and 32, and 24 is in between those. And fun fact, the trapezoidal approximation is the average of the left and the right ones. True story. You might notice, and we're going to use this fact later, that the f of 2 shows up twice in this formula. The f of 3 shows up twice in this formula. And like when we add all these things together, it's really like we're doing 1 f of 1 and 2 f of 2s and 2 f of 3s, 1 f of 4s. We'll see that, like kind of the details of why that works that way later. And it's like, sometimes the formulas look a little tricky. So Riemann sums are almost always written like this, and they will be on the AP test. They will be on my test occasionally, so you have to be able to recognize them. Basically, this is the sigma, and the important thing here is this n, which tells you the number of intervals you're going to use. Number of intervals. It's important that you understand this, so that you understand where integrals come from, which we're going to talk about in like a couple lessons. But this n tells you number of intervals. So if ours was there were 4 intervals, so ours would have been from 1 to 4, excuse me. But this tells you how many intervals there are. No, 3. Yeah, 1 to 3. This f of c, this f of x, these are going to be the heights. And this delta x, these are going to be the widths. And that's what this is. The Riemann sum is just a sum of a bunch of areas of rectangles. So I don't want you to like get thrown off by the sigma notation or by the word Riemann, which is just some dude's last name. Just understand that a Riemann sum is a sum of areas of rectangles. And they're normally the same. They're often, in Riemann sums, they're always the same width, I think. You can't really do different ones, but sometimes you'll be asked to use different widths, but worry about that when we get there. They're just the sums of areas of rectangles. And I know you guys know how to find the areas of rectangles, and I know you know how to add numbers together. So the mathematics of this is not that complicated. The concepts are more so, but we'll get there in a minute. So I like this little picture. It just kind of gives you, like another question is like, if I'm using rectangles, what's a way to better my approximation? So this here is a left approximation. Sorry, this is the blue one is a right approximation. And it's like not that great. There's like a bunch of missing space here and there's some extra space here. Maybe this would even out, but who the hell knows, right? If the curve looked different, it might not. And this is clearly 4. All right, there's 1, 2, 3, 4 rectangles. Now this red one is 1, 2, 3, 4, 5, 6, 7, 8 rectangles. In theory, it's the same curve. That's weird. This is like right or left. But the point here is that, I shouldn't worry about the right and the left. That seems to not be an issue. I like these pictures nonetheless, though. This has 4 rectangles. This one has 8 rectangles. The green one has, I'm guessing, 16 rectangles. Doesn't matter. More than the other 2. Can you even see if I write that in yellow? Not really. Let's do it in black again. This one probably has 32 rectangles. And the point here is this, that like there is some actual area under the curve. And like the more rectangles you have, the closer you're going to get to the actual area. My point is like, this is a huge empty space, and that's a pretty big one. But like when the rectangles get smaller, those like empty spaces and the overestimating pieces, like they become smaller and smaller and smaller to the point where like, if I had 64 rectangles, it'd probably be hard to even see the over and the under counting here. So we're going to use that concept later and the concept of limits to actually determine the area underneath curves, the exact area. So hope this was informative. Bye.